do an activity / talk on which is called Reading What Was Written, Coding Theory from Hamming to Reed and Solomon.
Yeah, okay, cool. I'm going to turn off my video because I'm going to write on my laptop, which means you'll be staring at the ceiling. But we will share screen.
I really wanted to see your ceiling, Dan.
It's not very interesting. It's the standard Stony Brook popcorn ceilings. Okay, so everybody able to see the screen okay?
Yep.
Sick. All right, yeah, so this is, I titled this Reading What Was Written. I figured just introduction to coding theory sounded pretty boring. So maybe this is melodramatic or cryptic, but nonetheless, maybe more interesting. So this is gonna be a talk about some coding theory. We're gonna try to make this as interactive as possible. So in particular, I'm gonna try to ask some questions that sort of lead you to develop this theory yourself. And then also feel free to interject with any questions you might have along the way. By nature of this being an hour, there's a lot that I can't really talk about, given this is like 15 years of development in a field. So I wrote up a bunch of notes. They're on the Math Club website if you want to check them out. They're like 12 pages or something, and they're quite a bit more complete than what this will be. But I'll try to touch on pretty much every section I have written down in there. Okay, so I'll start off with a simple question. So, oh no, my pen isn't working. That's annoying. Why is that? I'm sorry. That was really bad timing for that. I also can't read chat, so if anybody says anything in there.
Is it like needs to be charged?
No, I don't know what it is. This hasn't actually happened before. Huh, let me try one other thing. Yeah, so,
An alternative is to use the whiteboard feature on Zoom.
No, it's like my pen like just straight up isn't working. One sec, sorry. Okay, I could try this, I suppose. I don't know where it is. Oh, okay, I was making some of the notes. Oh, oops. Am I able to draw with my finger? Oops. Okay, what would be the backup plan B here?
You could go on Zoom on your computer and write with your mouse.
Yeah, I could try that. Okay, I could try drawing with my finger instead. That might work. All right. So maybe this won't be very legible. I could start off by writing something like this. Okay, so what does it say?
There's also a post-it in the center of your black screen. I don't know if
Yeah,
you
I
can see
know.
it.
I don't know how to move that. Okay, yeah, so what does it say?
Is it hello, how are you?
Yeah, exactly, right? but the thing is, I didn't literally write like, hello, how are you? Like I left out a bunch of characters in there. So it turns out that you're doing this process kind of in your head where linguistically, you know, some context of what's going on, and you're able to like fill in the blanks. So you're able to actually extract more information than I gave you, even though some like errors occurred in how I wrote this down. So we want to sort of generalize this process to how computers interact. And it turns out that this situation isn't so simple. In fact, here it's kind of astounding. We only used like what 60% of the actual characters in the full sentence of like, hello, how are you? Are you? So we actually like extracted more information than we were given. But for computers, we don't usually have this like linguistic context, or it's hard to encode or to convey this. And moreover, not everything we're going to be sending is like language anyways. So we need to figure out some alternative ways of doing this. In fact, the situation is much, much worse because we can't really do this in less characters. We're going to need more. We could think about compression, but under some underlying assumption that all codes or all messages are equally likely, we can't do any compression at all. Okay. So now this should arise some questions, right? So what would be the one question? I just said that computers have to do this differently. Anybody have any questions based off of what I said?
So the problem is to like take some message that might have missing letters and understand what it means. Is that the question?
Yeah. So there should be like two questions. One is like, how do we do this? So how to? This is sort of a qualitative question, right? Like we want to understand what processes we're going to use in order to make this happen. And then alternatively, we could do, we have this question of how much redundancy do we have to add? How efficient is this process going to be? So we could say how much. And this is going to be a more quantitative question. We're going to try to answer both of these. We're going to try to answer how we're going to do things, and then we're going to compare methods with some quantitative statistics on them. Okay, so then we could start off with some like general model of communication. Because before we understand how to encode and decode information with computers, we should have a decent sense of how our information is being sent and received. So first, the whole problem seems pretty simple, right? Like we're going to have some sender, and it's going to get encoded. It's going to get sent over some channel, maybe a wire in between computers or something like that. So I'll label that as C. Then it goes and gets decoded. And finally, you have some receiver who gets the message at the end. But things aren't this simple in the real world, right? This is a good idealistic model, but oftentimes there's going to be noise over this channel. That what we receive might get corrupted. So you can model this by adding another block. So this is going to be noise, and it shoots into the channel and changes what is actually being received by the receiver. Okay, so then we could think about a few examples of this. I think it's useful to try and understand what this model is really saying. So we can start off with the example that kind of started this field of coding theory. In a little bit, we'll talk about Hammon codes. Richard Hamming wrote programs for the Manhattan Project, where he would do some calculations with computers that couldn't really be done by hand. And then later, he went on to Bell Labs. So part of what happens with the really old computers is you can't really program them. There's no like GUI. There's not really a command line. So you would encode things on punch cards. So it's a literal card with a bunch of characters on it, and then you punch out some of the holes, and then through some like electromechanical process, the computer is able to read these. So this is part of why like old Fortran is really weird. One of the problems with this, though, is there's a bunch of ways that this punch card could get messed up. It's paper, so it's kind of flimsy. Maybe you misaligned the punch, something like that. So sometimes computers at like Bell Labs or at the Manhattan Project would read these cards wrong, and the whole program would crash. And what happens is this is kind of annoying, right? Because if you're putting up a huge program and then you're about to, like, you go home for the weekend and wait for it to run and you come back, you'd be pretty mad that your entire weekend was lost time and now you're going to have to spend your whole week trying to redo this calculation. So he invented this theory of Hammon codes. So if we go back to the entire model, right here, the encoding is the program. And then the program. And then, or sorry, the sender is the programmer. And then the encoding is the punch card. The punch card goes, or punching, I guess, would be the encoding. Then the punch card is like the literal channel. And then it goes and it gets decoded by the computer. And then finally, the computer actually runs the program. And the noise here can be a whole bunch of different things, because punch cards are really bad. Right? It could be that the paper's flimsy. It could be that the paper wilted. It could have some just random incorrect reading through the electromechanical process, et cetera. So there's a myriad of different issues that could arise here. So maybe another example that's probably more pertinent to what we're going to talk about is DVDs and CDs, right? So like an example would be my favorite movie when I was a kid was Monsters, Inc. And I watched it tons of times in the car or at home or whatever. But kids are stupid, so I didn't take the best care of my possessions, and those DVDs, like for Monsters, Inc., got scratched all over. However, they might skip or something, or like the volume might be messed up or something. But these things actually still play pretty well, right? Like you can generally tell what's going on unless the scratch is super, super major. This is because CDs and DVDs have this built-in error correcting technology. They're going to be what we build up to. They're called Reed-Solomon codes. And Reed-Solomon codes are kind of the king of like applied coding theory. They're really useful. They're in CDs, they're in DVDs. They're what we use for like the Hubble Deep Space Telescope, stuff like that. They're absolutely everywhere, and we're going to try to have this as like the magnum opus of the talk. All right, so before we do that, we have to talk about some algebraic preliminaries. So since it's kind of annoying to write without a pen, maybe I won't be writing things out as much as I would like to, but we're going to have to develop a language in order to talk about our codes. Okay, so we're going to let G be a set, and then we're going to have some operation on it, plus. So we're going to say that G is a group if the following is true. So for any F, G, and H, we see that F plus, then in parentheses, G plus H is equal to F plus G, and then out of parentheses H. This is associativity, which you talk about in like middle school and high school and stuff. Okay, and then there's going to be this element 0, which is the identity, where we have that 0 plus any element is equal to that element plus 0, and it just spits out the element. This is our pretty much normal notion of 0. And then finally, for any element G, then there exists some element minus G, such that G plus minus G is the identity. Okay, so additionally, the group is called abelian if we have this fourth condition, a commutativity, right? So that just says that G plus H is equal to H plus G for any G and H. I should probably note that this notation of using plus as the operation is generally reserved for this abelian case, but we're only going to really be talking about abelian groups. So it doesn't particularly matter. I think it's more confusing to just add more notation. All right. So there's a bunch of examples of groups that are pretty familiar to us. So one that we'll talk about is, very briefly, is the integers with the normal notion of addition. So this is just the set of all the negative whole numbers, and then it goes all the way to infinity over here too. And then plus is defined in the normal way. This is maybe the most important group for a lot of cases when you're learning algebra. And in fact, a lot of time you spend in an abstract algebra class is pretty much saying, why isn't this structure as nice as G? And then adding some more structure to make it as nice or nicer than Z. But we're doing some applied stuff. We're doing like computer science or electrical engineering here. So we're going to be mainly interested in like finite objects, particularly those relating to the number 2. So for that, we're going to introduce something based off of Z. Oops. This is going to be called the cyclic group of order n. Of order n. And it's denoted by Z mod 2, mod nz. Okay, so what is this? The underlying set for this is just 0, 1, and it goes all the way up to n minus 1. And then we do our addition in the normal way for modular arithmetic. So I said that like this Z mod 2Z thing is going to be the important case for us. So maybe we'll do the example for that. We'll write out all of the operations in here. Okay, so Z mod 2Z, the underlying set is just going to be 0 and 1. And then we have 0 plus 0. Well, that's 0. 0 plus 1 is equal to 1. And then 1 plus 0, that's also 1. And then 1 plus 1, well, that's equal to 2, right? But 2 mod 2 is just 0. Okay. So addition is nice. But like what's missing here? What do we want generally? Like when we work with real numbers, addition is okay, but what else do we want?
Maybe multiplication.
Yeah, exactly, right? So there's this notion of multiplication with these objects called rings, but we're not going to really talk about them. It's kind of a okay version of multiplication, but we're going to focus on this nicer version of multiplication with objects called fields. So we're going to find these two now. Okay. All right, so we're going to let F be a set this time, and it's going to have two operators. It's going to have a plus operator and a times operator. Then the set is called field if the following is true. So the first condition we put on here is that F with the operation of plus is an abelian group. So we're also going to want to put this group structure on multiplication. What's the immediate problem with putting group structure on F using multiplication? So if I write down like F times, what's messed up about that? Okay, I can just say, all right, so it gets messed up because we can't really like divide by 0. Oh, if there's stuff in chat, I should have it pulled up. Yeah, dividing by 0 is undefined. Exactly. So we need to get rid of the 0 thing in here, and then we can say that F minus the 0 point is also an abelian group. And then the final thing we want to say is that these two operations play nicely together. So this is just the distributive law that you also see in like a high school algebra class. So in particular, it says that G times F plus H is equal to G times F plus G times H. So fields are really what we're going to be working with most of the time. They have some nice sense of addition, subtraction from the addition being an abelian group, and then we also have some nice version of multiplication and division from like F times being an abelian group. We can do analysis on these things. We could do some nice like linear algebra, which we will, and now we could look at a few examples of this. Okay. So the two examples that you're probably most familiar with are Q and R. Great. So Q over here, that's the familiar thing where you just have like P over Q, where so P is some integer and then Q is some strictly positive integer. And then we have that like this is in some reduced form, right? This is pretty natural to think of algebraically, right? We're just like taking like these formal symbols of P over Q and then defining some equivalence relation on them. These are things that might be less obvious how we're going to think about them algebraically, and that's because these aren't really nice, or these aren't natural algebraic objects to think about. In fact, there's like no purely algebraic construction of R. So this Q example is a lot nicer in some certain algebraic sense. Okay. So now I said before that we're going to be primarily caring about these finite things. So let's start off with Z mod 2Z again. So this time we're going to give it some plus and times, where this times is in the usual like mod n way as well. All right, so then if we just go through this, 0 times 1 is 0, 0 times 0 is 0, 1 times 0, that's also 0, and then 1 times 1 is 1. And that's okay, right? So is this a field? Yeah, okay. Yeah, so this is a field, right? But we're caring about like powers of 2, right? So maybe it's important to think about if this is always a field. This is U mod NZ thing. For that, we could look at a power of 2. We could look at, say, Z mod 4Z. Okay, well, Z mod 4Z, we could start off and everything's the same. 0 times 0 is 0. 0 times 1, well, that's also 0. We keep going. And then eventually we run into this thing where 2 times 2, that's 4. But this is mod Z, or mod 4. So this is 0. And like this can't be right? Just using our intuitive definition, or sorry, intuitive knowledge of like multiplication through real numbers and stuff, this doesn't seem like it should happen. We shouldn't multiply two non-zero numbers and get 0. And in fact, this is against the field axioms. I won't prove it for the sake of time, but you could take it on my word or prove it for yourself that this is indeed bad. So does anybody know when this happens? When is Z mod NZ a field?
When n is prime.
Yeah, exactly. So that's going to be a theorem that's kind of important to us later. Is Z mod NZ with these like naive ways to define plus and times. So that's a field if and only if it's the case that n is some prime. Yeah, I won't prove this either for the sake of time, but this is all. This is in those notes if you want. It's not a particularly difficult proof. Okay, so we've shown that Z mod PZ is a field, and this is going to be, we're going to write it instead of Z mod NZ because I don't feel like writing 4 characters every time. And particularly Z's are annoying. So this is going to be written as GF2, or sometimes you might see it as like Blackboard F2. This is like Galois field of order 2. As you can see, like in the notes, I probably won't go into the Galois theory, but this is because we'll develop some notion of other finite fields that have a lot to do with Galois theory. So this is going to be called we'll call this like the finite field of 2 elements. Okay, so it's probably an important note that these like plus and minus, or sorry, plus and times operations that we've defined on Z mod 2Z in particular should seem familiar to any like computer scientists or electrical engineers. In some more computery terminology, this plus, which maybe I'll just circle, is the exclusive OR, and then this times is an AND operation. So this is kind of important. It shows that these have like a very nice representation insofar as computers are concerned. And in fact, these are really basic operations for digital systems to do, which means that a lot of the things that we're going to talk about can be implemented decently efficiently. All right, so now we have some algebraic tools to talk about things. And we'll talk about like the most basic example now, which are called parity bits. I again apologize for the terrible handwriting. I don't know why my pen decided to not work. All right, so first we're going to talk about these in maybe a more intuitive way, maybe how like an engineer thinks about them. And then we'll talk about them in a more mathy way using the algebraic tools over like GF2 that we just thought about. Okay, so one way to think about parity bits is we're just going to count odds and evens. So if I write down the string 0, 1, 1, 0, we can count up the number of ones, and there's an even number of ones. So we'd say that this has an even parity. Okay, so what about like 1, 0, 1, 1? What would that have? Okay, that's an odd parity. Okay, so now we can define a bit based off of these, which kind of like signifies or encodes this information that is either an even or odd parity. So if it's even, maybe we'll say P of like some bit string B. Well, if it's 1, if it's an odd, if the string has odd parity, and it's 0 if it has even parity. Okay. So maybe I'll write down an example quick. So if we have the string like 0, 0, or 1, 0, 0, 1, this is going to have even parity, so the parity bit would be 1. Maybe I'll just write it out front, separated by like a semicolon, so you can see that. All right, so as another example, if I write down this string, what would be the parity bit? Does anybody want to? Okay, so this has an odd number of ones. So the parity bit would be 1 out here.
So would the parity of 1001 be 0?
You're right. Thank you for correcting that. I can't count. All right. So now, actually, that brings me to the next point. So if I write down what I had just written down, 1001. So as Mark just pointed out, there's like something wrong with this, right? We can obviously tell that there's something wrong with it because, well, we count the parity of the string, well, and then we say, well, this should be 0, but it's not. So either this parity bit got messed up or the message itself got messed up. In particular, which is the case here? What got messed up? The parity. Well, so it's the parity. You could, I guess, say that it's the parity that messed up because I wrote it down that way. I messed up while I was writing it. But if I just say that like we received this message, what's got messed up? The message or the parity? Does anybody want to? Yeah, exactly. You don't know. Cool. So that's sort of the limitation of this is we can detect if one error has occurred, but we can't actually do anything about it. We don't know what's happening with this. I guess there's another thing. What is the other part that's kind of wrong about these codes? Like what happens if what happens if I also so we said this is wrong. What if I make this a 1? Now it's double wrong, right? And we could, but it looks perfectly fine. So this parity check, we're adding 1 bit and we can tell if 1 error has occurred, but we can't tell if 2 errors have occurred. Moreover, we can tell if 1 error has occurred, but we can't actually do anything about it. We can't correct it. So that leaves us two Hammon codes. And I should preface this by saying that Free Blue and Brown just put out 2 really, really good videos on Hammon codes. And if you haven't seen them, you should check them out. And it takes him like 36 minutes. And I don't have that much time. And I can't hope to possibly cover them as well or in the same amount of time as him. And certainly not both of those. So I'm going to kind of do a quick and dirty overview of these. And if you want to learn more about them, I'd very highly encourage you to check out those 2 videos. All right, so now we know about parity bits, and we can detect if precisely 1 error has occurred. And it's not too hard mechanically. It would be pretty difficult to come up with, but the machinery itself is not too hard to be able to detect and correct an error. So we're gonna, like I said, we're gonna do a sort of quick and dirty version of this, but what we wanna do is dissect what's going wrong with our code. So we're gonna consider sending 7 bits. So it's like B1, B2. Is it clear what I mean by this? This bit string? Okay, I'll assume that that's clear. All right, anyways, so yeah, we have this bit string and we're going to want to do log of n+1 checks. So in this case, this is log of 7 + 1. This is a base 2 log, like pretty much anything in computer science. But anyways, so we're doing log of 7 + 1, and that's just equal to 3. So we're going to do 3 parity checks. And my claim is that we're going to do this in a clever way so that we could actually detect and fix an error. So we could write this down sort of conveniently in a Venn diagram for the 7-bit version at least. So what we'll do is we're going to say that x1 and x2 and x4 are the parity check bits. This is going to be the redundant information that we encode. And then in here, we're going to have x3, x7, x6, x5. And what we want to do with this is we want to make it so that each of these big circles, maybe I'll draw them in a different color to make that more clear. So each of these big circles should have an even parity. And we can choose x1, x2, and x4 so that it does, in fact, have even parity. And what this says is, so let's say that this red circle is fine. This green circle, and then we'll keep that as the blue circle. So if I receive a message and the red and green circles have even parity, but the blue circle has odd parity, what does that tell us? Anybody know? Or anybody come up with some algorithm for us to figure this out?
Wait, what is this circles?
Okay, sorry. Maybe I could redraw these quick. Okay, so we're gonna have a red circle. We're gonna have a blue circle. I think I changed them around, but it doesn't really matter. And we're gonna have a green circle. And each of these circles is supposed to have an even parity. In other words, if we think about each of them, they should all they should add up to 0. So if I receive a message and say, okay, so this does have even parity. This also has even parity, and this has odd parity. What does that tell us? Are we able to figure out what went wrong?
Well, yeah. You know the error can't be in the blue circle or the red circle, so it has to be in the green circle, and so it has to be x1.
Yeah, exactly. So that's going to be like our general way to figure these things out, is that in this Venn diagram representation, which is like particularly nice in here, we're able to know, or we're able to kind of dissect what's going on by looking at where things went wrong and where things went right, and figure out where our error is. So what we just invented is called the 7-4 Hammon Code. Anybody know where the 7 and the 4 come from?
Is it because you have like 7 X's and there are like 4 of them in each circle?
Yeah, so this, no. Okay, so the 4 is slightly off, but the 7 is exactly right. So it's because we're sending 7 bits. Anybody else want to say where the 4 comes from? That's a good guess of the 4, but it doesn't like hold for other examples.
Could you like scroll up so I can see better?
What's that?
What you drew? Could you like scroll up so I can see what you drew a little better?
Good thing. So I guess as a hint, in particular, I said that we choose these x1, x2, and x4 based off of the other values. These are our redundant values that we have to code in.
Does 4 like represent the actual number of bits that carries information?
Yeah, that's exactly it. So this 4 is like the useful bits. This is how much information we're actually sending to the receiver.
Which are the useful bits besides x1, x2, and x4?
Oh, I'm saying x1, x2, and x4 are the unuseful bits. So maybe useful is a misnomer here. What I mean by useful is that the message itself is actually the x3, 5, 6, 7.
Okay, so like the message itself is, I mean like the chunk of the message is like x3, x7, x5, x6, but like and like x1, x2, and x4 are just like telling us if there's an error, basically.
Yeah, exactly. So in the lingo, the x1, 2, and 4 are redundant. There's some they provide some redundancy for the actual message, which is like x3, 5, 6, 7.
Okay.
Okay, cool. So one of the big questions before was a quantitative question. We wanted to say, how efficiently can we do this process? So what is sort of a natural, maybe I'll scroll up to be a little bit more suggestive. What is a sort of natural method to say, how efficiently are we doing this? How efficiently are we encoding information?
Like what percentage of the thing you're sending is actually useful?
Yeah, exactly. So this is
like 4/7 would be for that one.
Yeah, that's exactly it. So we're going to let C be some code, and then we're going to say that where we send a total of n bits, and k of these are like the useful bits or the message bits. Well, then we're going to define the rate of C as just k over n. It's going to be the number of message bits over the total. Okay, so like Ajmain pointed out, for the Hammon codes, this has a rate of like 4/7. So this is about 57%. So anybody remember how many, like I said that these Hammon codes, we could have a variable number of n. Anybody remember how many parity checks I said they use?
You say log n?
Yeah, it's like log n minus or log n plus 1. So same thing. So this actually scales really well, right? Because this should be, so if we're sending a total number of 2 to the n bits, well then our parity bits are, they scale like log base 2 of n plus, sorry, this is wrong. So if the total number of bits is 2 to the r, then the number of parity checks scales with r, right? So this is like r minus 1. Should be 1 over 2 to the r. And this is the rate of some general like 2 to the r minus r minus 1 Hammon code. And so what is the limit of this? What is the behavior as I make r really, really large?
100%.
Yeah, exactly. So like even if we go to something like a 255, 247 Hammon code, this is already this already has a rate of like 97%, which is really good, right? And you could say, why don't, well, most messages are much longer than 255 bits. So why do we even care about making this longer, right? Or why do we care about other methods, right? This tends to 1 and it does it actually pretty quickly. So there's one big reason why. Does anybody have any ideas? So how good was the Hammon code at correcting things? Yeah, that's exactly it. So the ability to detect multiple errors, right? So the Hammon code was only able to detect 1 error. And this is fine if you're sending like if you're sending 7 bits, then this is okay. Like we only have there's a pretty low rate of transmission, or sorry, a pretty low rate of error for a small number, or for any good communication system. So this 1 error thing isn't a big deal if we're only sending 7 bits. And likewise, it's not a big deal if we're sending 255 bits. Like most computers should be able to handle that nowadays with only really changing 1 bit max. But the problem arises when we have like these astronomical numbers, right? So as R gets very big, then the rate, we could still only fix one error, but the probability of one error or of like 2 errors occurring gets bigger really quickly. And we want to quantify this as well, another quantitative measure. So this leads to another question. If I write down 2 strings, maybe these aren't necessarily bits, but they can be. So sorry, these should all be ones. So if I write down like A1, B1, C1, D1, and I write down another message, A2, B2, C2, D2, how do we measure how different these are? Or maybe it helps if I write down some other example. So like if I send, or if I have these messages tree and maybe these 2 characters get switched, how different are these?
I would say they're pretty close.
Yeah, but do you have like a number for this? What would be your immediate reaction if I said give me a number?
I would say either 1 or 2.
Yeah, so maybe this isn't the greatest example because the switching thing maybe makes you think 1, but 2 is a pretty good answer as it turns out. So we can say that these are precisely 2 characters different. And so what would the generalization of this be to like this general message I sent? How would we measure?
Oh, I just realized like these ABCDs, they're just zeros and ones, right?
They can be zeros and ones, or they could be other characters. It doesn't matter. If it helps you think of them, you could think of these like AI as being zeros and ones, or you could think about them as being like in the alphabet, A, B, C, D. Either one is fine. But yeah, so how would we generalize this to see how different these 2 strings of letters are?
Well, I mean, if you only had 2 letters in your alphabet, 0 and 1, then you could just count the number of places that you have different characters. So then, in these specific positions, you have different characters, so you just have to flip them. But if you have more than 2 letters in your alphabet, then you can't just do that. So there's more complexity. So I don't really know.
Well, you can just do that. So I mean, maybe it's not the best measure. Maybe we'll say that, or maybe we could say that like tree is closer to TTRE or than it is to like TQZE or something. But we don't necessarily have to. We make the definition off this like naive case that you pointed out. So we're gonna let X be some code word. So this is like X, or some message rather. So this is like X2, and this goes all the way to XN. And then we have like Y be the same thing. So this is Y1, and it goes all the way to YN. And then we define this thing called the Hamming metric on these 2. And the Hamming metrics, maybe I should write X, the Hamming metric on X and Y is equal to the number of characters that are different. And I claim this is actually a really good definition. And one of the reasons why is you can do some pretty good analysis in geometry with this. So for anyone who has a background in here from like MIT 320, you deal with a lot with metric spaces. And this is a legitimate metric on the space of code words. We could show the triangle inequality, and then the rest of it's not too hard. In fact, if we embed these, like if we have bit strings and we embed them in Rn, does anybody know what metric this would be equivalent to?
Taxi cab?
Yeah, that's exactly it. This is a restriction of the taxi cab metric in the binary case. So that fact in particular isn't too important for us, but nonetheless is it's kind of neat. So now we know about the Hamming distance. How does this relate to like telling code words apart? So when are 2 code words different? So when are two received code words X and Y different? Well, it's just like when DH of X and Y is greater than 0. And then we can say how different they are they? Well, we created this measure to quantify how different they are. So with parity checks, for example, so if we swap one bit in the message, well, then both that bit and the parity check will swap, right? Does that make sense? In other words, if I have some message, so like the parity is 0 and it's 1010. Well, if I change one bit, maybe for example, it's this 0, 1. If I change this to a 1, well, then the parity changes too. So in particular, what this means is that the distance, what is the distance between any two valid code words? Anybody have an idea of what the minimum, or what, sorry, what the distance between any two code words is? Or the minimum distance between any two code words?
Wouldn't the minimum be 0 since it could be the same?
So you're right. But if I say X is not equal to Y.
Then 2.
Exactly. So then we say that dmin for this parity check system. So dmin, oops, didn't mean to change colors. So dmin is equal to 2. Well, what this means is that we could like tell when something isn't a code word, but we can't actually say what it's closest to. If we we could geometrically think of this, right? So if we could think of this as like some cube. So this would look something like this. So this is like the 0 string. This is 1, 0, 1, and then it goes up. So then this is another character, and then this is another character. And then the sphere that we around, say, this red point, well, the sphere around it, we could just draw around. Sorry, so this goes like this. We can see pretty clearly that we have like a distance to any given code word. So if something's over here, we can tell that it doesn't overlap over here. But if we get this distance to be larger, then we could say, okay, there's a clearly defined closest element. And then we could actually assign that code word to the closest element. So in the 7.4 Hammon code, if we change a bit, at least 3 bits change since use of the parity checks, or since it belongs to at least 2 parity checks. So the minimum distance there is 3. So what that means is if we draw two spheres, or so these are a distance 3 apart. So the radius here is 3. And then if we have some point that's like a distance 2 away, well, then it's closest to, sorry, if this is a distance 1 away, then it's closest to this point uniquely. Since the minimum distance is 3, well, then we use the triangle inequality and we figure out that this code, or this vector X, is closest to this vector Y. It's further away from Z. So then we could use this thing called minimum distance encoding. We say that in this geometric space that we define, we go to the closest code word, and that is going to be what we say the message is. So I have a picture of this in the notes. I don't think I have time to write it out, unfortunately. running kind of low on time. But nonetheless, if you want some more geometric intuition on this, you could check that out. Okay, so as some people have probably figured out, our strings are sort of our bit strings. We could think of them as like vectors, right? They're vectors in GF2 n. So this is an n-dimensional vector space over the field GF2. We could define this theory of linear codes, which like Gus Solomon and I think is Levi Reed, they helped found this idea of linear codes. So what do we care about linear codes? One is that this is all dealing with computers. So we want things to be very efficient. We want to be able to listen to music right away off of our CD. We want to be able to send a text to a friend instantaneously. And linear codes, for one, have a very efficient way to be written down, which is one reason we'll care about them. They lend themselves very well to circuit methods instead of having to compute all these things with the computer, which is slow. We can just do them in hardware, which is fast. And finally, it just turns out that pretty much everything useful that we want to define can be defined in this linear way. So I'm going to give a very, very brief overview of linear codes just for the sake of time. But again, there's a more complete overview of them in the notes I wrote down. All right, so we're going to say that we have this code C. It's going to be inside of this vector space Fn of n-dimensional code words. So moreover, we're going to say that this is a linear subspace of dimension k. Then we're going to call this an nk linear code. And in fact, we're going to use this bracket thing pretty much exclusively for linear codes. So kind of...
how is a code a subspace?
So this code, like these codes are, this is a set of all different code words. So all the
these
different...
are the valid ones, or?
Yeah, these are the valid ones. So all of the valid code words are bit strings of length n.
It's not clear to me how it's a subspace, but you can go on.
So yeah, okay. It's not particularly clear how it would be a subspace immediately. But what does it mean to be what does it really mean to be linear on some vector space?
You have like its closure under scaling.
So that's one way to think about it. Like more basic, or maybe not as basic, or maybe not as simple in terms of math, but like you don't really think about like these general linear maps in an intro to linear algebra class. What do you think about? Or in particular, you think about linear maps in terms of a basis, right? In which case we could represent them as what?
Matrices.
Yeah, that's exactly it. So we could, so for a linear code, we're going to have some representation X, which maps some message to a code word. So in a way, this matrix is like generating the code. Generator matrix. So we'll call it a generator matrix. For the sake of timing, and I won't go too far into it, but this generator matrix, it's really just any like k by n full rank matrix. And all of the codes that we've examined so far, the Hammon codes and the Parity Check bits, both have pretty nice generator matrices. So then there's also some talk that we could do about like this thing called the dual code, and like the dual code, and we could talk about like the generator matrix for the dual code. But yeah, check out the notes if you want that. I am quickly running out of time, and I want to talk about reselling inputs quickly. All right, so we saw that the Hammon codes have a very good rate, but they have an issue with the minimum distance. But we can do this kind of dumb thing, right? We could just like repeat. So if we have some message M, we can just repeat the bit over and over again. And this gives a fantastic distance. It gives the best possible distance, but it's really stupid, right? Like it's really inefficient. The rate is like 1/n, which is awful. So there's obviously some trade-off between the rate and the minimum distance. And it turns out the best case in a lot of practice is the Reed-Solomon codes. This is like really a family of codes, and there's a bunch of different variants, but we're gonna very quickly talk about the sort of thing that the way that Reed and Solomon might have thought about them. So really quickly, if I just write down a point, like what would be the line going through this point? We can't really define it, right? Like this is a line, this is a valid line, this is a valid line, etc. We need 2 points, and the same thing. I could draw this parabola, or this parabola, or this parabola, and they're all valid. But as soon as I draw in this third point, then the parabola is fixed. This is some general theorem. And the general theorem is that a polynomial of degree n is determined completely by its evaluation on like n+1 points. So the idea here that like Reed and Solomon had were to exploit this principle. So yeah, I'm already over time. So just very superficially, if we have some message M, and we'll say this is like M0, M1, all the way to M K-1, because we're sending a message of K bits, or sorry, K symbols. They're just gonna turn out that they're not really bits. Well, then we can encode this as some polynomial. So we're gonna write Pm of X. And this is just going to be, we're gonna interpret it as coefficients of the polynomial. So this is like M1 X, and then this goes all the way up to Mk-1 of X to the K-1. And then we want to interpret it, we want to write down, we want to completely determine this polynomial by evaluating it on some certain coefficients. What's the problem here? Why did I say that this can't be bits? If we want to evaluate it, so Pm of X, this is a polynomial over our field F of degree K. So like why is it a problem for us immediately to say this is a binary code? Does anybody know? Well, the thing is that if this is F2, or sorry, this is in our F. So if this is F2 or GF2 or whatever, we can't actually evaluate this at K different points if K is any larger than 2, right? It doesn't work because we only have 2 points in the field. So the solution to this is to evaluate at n different points. And for that, we need to use some different field, GFN. But this turns into a problem. Before we said that we only had like Z mod PZ being a field. And it turns out through some Galois theory, which I also put like some superficial account of in the notes, then we have GFN exists for n being some prime power, p to the r. In particular, since computers like these 2's, like the 2 to the n things are fine, we just use like GF 2 to the r here. And this is kind of the math punchline of this, is that like Solomon and Reed were two computer science or two electrical engineers. This was 1960. There wasn't really computer scientists per se, but they took some things that were previously pretty simple math-wise, and instead they kind of ventured into pure math. And looked at these Galois fields and did some kind of crazy math in order to come up with what ended up being our main method to encode and communicate information. I guess that's
Solomon was actually a mathematician. He wasn't like his
Oh, was
background. He got his PhD in math. Yeah.
Okay. I guess most of the time, people who care about coding theory are like electrical engineering, electrical engineers. But yeah, okay, he was a mathematician. Sorry. Cool. Yeah. So anybody have any questions? I guess I could say quickly, the reason why I talked about the linear codes is also that this Reed Solomon thing is linear code. So if we have like primitive elements of our field, we could write down it's like the transpose of the van der Waals matrix as the generator matrix, at least in this form. There's some nicer forms, but. Okay, cool. Yeah, so anybody else have any questions?
Thanks so much for the talk.
Yeah.